And this is now just doable, right? By the fundamental theorem of calculus. Ethan, wake up. The integral of cosine u is just sine u. And so what I get is sine u evaluated at pi and pi over 2. And is everyone following me here? And then this is 0 minus sine of pi over 2, which is 1. And so the answer is negative 1.
Wait, how's that like a... It's very, very similar.
It's very, very similar. In one case, I have an integral that I need to solve. So I stop everything, solve an antidifferentiation problem via substitution, substitute back in, and then apply the fundamental theorem of calculus. Lame. Cooler is, here is an integral. Let's just transform this integral into a different integral. And then I never go back. I don't ever do the back substitution. So the claim I'm actually making here is that this process makes sense, right? The claim I'm trying to make is that the integral from pi over 4 to pi over 2 of 2 cosine 2x dx is actually equal to the integral from pi over 2 to pi of cosine u du. And therefore, by doing this integral, I also do this integral. All right, now I've picked a function which is easy enough that we should be able to have a picture of this. So let's do that now. Let's make a graph of 2 cosine 2x on the interval from pi over 4 to pi over 2. Well, let's let this be pi. The amplitude of this function is going to be 2, so I'll go 1, 2. And let's see, what's the period of cosine 2x? Pi. It's going to be pi, right? So we got a little bit of this. So to graph this function, it will look like, it's just kind of pre-calc A skills. It's going to look like that, I think, right? That is 2 cosine 2x. And the integral from pi over 4 to pi over 2 is that shaded region. So by the way, knowing that the area under one hump of sine or cosine is 2 means I could have just done this problem by thinking, right? Because what would be the area of this entire hump?
2.
Oh, actually, it's kind of complicated. No, I think you're right. Well, okay. All right. So there's two things going on here, right? I have this hump, which I'm compressing horizontally by a factor of 2. But I'm also stretching it vertically by a factor of 2, right? So Chris was right? The area under one hump would be 2. Because I pushed it this way and made it smaller, but then I stretched it this way and made it bigger. So therefore, half of a hump is going to have area 1, and therefore that makes sense that this integral would be negative 1. Do you agree? Okay, now notice what's going on. This is like the x-axis. These are x values. What I'm now doing is I'm literally transforming the x-axis into the u-axis. And the formula for how the x-axis is to be transferred into the u-axis is this formula right here. Everything becomes stretched by a factor of 2. And when we want to understand why this integral equals this integral, well, now I'm going to graph this function, cosine, on the interval 0 pi. Well, cosine on the interval 0 pi is going to look like that, right? You guys with me? And I'm going from pi over 2 to pi. And thus, that integral on the right is like this, is like that area, which I can also convince myself that that must be negative 1, because again, it's just half of a hump of a normal cosine curve. What's missing here is like the 2, right? Because it hasn't been stretched this way or compressed this way. So do you guys see visually how these are the same? So what I'm really doing when I'm doing this substitution, this is deeper than just doing some little variable switcheroo. What I'm really doing with this substitution is I'm defining a new function u, and this is now, whereas this was the x-axis, this is like the u-axis. and I am transforming the entire integral by stretching it out by some kind of factor according to some function, and then adjusting like based on the derivative. That's just kind of like what's going on with the 2dx. All right, so I don't know. This is a lot of talking. Do you guys get this? Should we just maybe like do a problem? Let's like do a problem in the book. Oh, that's like the whole point. The whole point was option number 2. Yo. What? Oh yeah, you can just leave that there for a second. Let's do a problem. Let's do. Oh yeah. Okay. So let's do a problem. Integral from 1 to 5 of x over root 2x minus 1 dx. Should we just do it like semi together?
No.
No?
Okay.
I feel like we should do it semi together.
No,
What's
wait,
your? Can we just pick
wait,
you?
hold
Can we pick you together at least?
Yeah.
Can we just let u be 2x minus 1? Because I feel like that's just like a good idea. If you did anything different, then it's like a bad idea. So let's like do that first.
It's down here. Dx is equal to d over 2.
Oh.
So far you just kind of like do the old things that we used to do, right? You put the 2 in here. This is how I do it at least. You put the 2 in here and you undo the damage with the 1/2, right? Is that stupid? What? So far good? Ethan, you with me?
Should have made a root to write my name.
No, I don't think so. Well, I don't know. Maybe I should have. You think so?
Yes.
I don't know. Anyway, I think it works either way. So now I'm ready to change this integral from x's to u's. But the moment at which we change it from x's to u's, so this is 1/2, this numerator becomes du. No, Ethan, I disagree with you. I like my way. It's great.
My way is pretty great too.
This numerator is du, and the denominator is root u. But the moment at which I change it from an integral in terms of x's to an integral in terms of u's, what happened? Oh, crap. So I changed my mind. This is not as easy as I thought. But it's still doable, right? Because what is x? I get u plus 1 is 2x. So x is just u plus 1 over 2. Okay, but now this is a little bit of a drag. Maybe Ethan's right. I don't know. We'll find out. So this is, so I have a u plus 1 over 2. But at the moment at which I change it from an integral involving x's to an integral involving u's, I have to also change the limits from x values to u values. So this becomes u of 5 and this becomes u of 1. That's kind of the crucial moment. Everyone following me? Okay, now I just continue. Let's take out that 1/2. So this becomes 1/4 the integral from, what is u of 1? 1. And what is u of 5? 9. And then this integral becomes the integral u plus 1 over root u du. Well, that's not so hard, right? Really, that's just 1/4 the integral from 1 to 9 of u to the 1/2 plus u to the negative 1/2 du. And the nice thing about this approach is there is no substituting back. Now I just do that integral just as is. So it's going to be 1/4, and the integral of u to the 1/2 is 2/3 u to the 3/2 plus 2u to the 1/2, and I evaluate that at 9 and 1. Jesse's making sense? Newman? All right, and now I think this is just not so hard to do, right? It's 1/4 times, that's 327, so that's 54/3. Oh man, did I mess up again? 9. Wait a second. Oh yeah. So that wasn't wrong when I said it was just dumb, right? So 3 cubed, 27, 9, 18 plus 6, that minus 2/3 plus 2. So whatever that is, 24, 22 minus 2/3, so 1/4 times 22 minus 2/3. 66, 64/3, 1/4 times 64/3. So I got 16/3. Alright, how are we doing on this? What's up, Chris? You did it wrong, but you see what I did?
No.
Nancy, you don't see what I did?
I mean, I see, but I don't understand. It's just not like.
Yeah, you're converting from one variable to another. And when you convert the equation, you have to convert I guess my main thing to do is just please form an emotional connection such that when you see these numbers up here, you should think of these numbers 1 and 5 as x values. These are x values. When the integral changes, variable, so must the numbers change. If these are x values, I need to convert them into u values because now I'm integrating with respect to u. Does that make
I was
sense?
thinking that you're multiplied by u, but it's actually
Not multiplied by u, I'm
inside of it.
That's right, because I'm trying to encourage you to think of u as a function. Yes, I'm not multiplying by u. I'm plugging 5 into u. I'm plugging 1 into
I
u.
get it.
Oh, Chris gets now. Good. All right. So, Teacher of the Year. Where are my dumplings? Teacher Appreciation Week. Chris.
Is it this week?
Yeah, all week. No, it's over. It's okay. I will pick up this later. All right, 3 more things I wanted to do today. One is this packet, which is pretty exciting. Oh, there's 4 more things I want to do today. Can you give everybody one of these? We're going to do just one of these problems, and you're going to figure out all the rest by yourself. So, the first problem on this packet says, take the limit as n goes to infinity of 1 over n times 1 over n squared plus 2 over n squared plus 3 over n squared plus all the way up to n over n squared. Okay, and what you're supposed to do, David, professionals like just count out 4, drop it on the table and move on. Much more efficient. You're gonna take 10 more minutes. Yeah. All right. So, how do I do this? Well, this is basically just a test of your understanding of integration, right? We actually did a problem like this already. So, what is this? This is going to be some kind of integral, right? How can we figure out what integral it is? Or maybe you just already know.
So
I have-
white paper.
I have to like reverse engineer a picture.
You know what I'm saying?
I have to reverse engineer a picture. What appears to be going on here? Eleanor, what appears to be going on? Just like talk to me. Use the word Riemann sum.
It's a Riemann sum.
Yeah, it is a Riemann sum. So what kind of Riemann sum though? Like talk to me. Like what are the, like, I don't know.
It's like square.
I is over N.
Yeah?
It's squared.
Yeah, it appears as if we are squaring numbers, right? So it seems as if perhaps the function is like x squared. And what else does it seem like? What are we skipping by each time? Yeah, Chris says it also appears that we seem to be skipping by 1 over n, right?
Yeah.
And actually, I think that's just right. Okay. Now I'm gonna just draw a picture. So basically, what do you just think the answer is?
The sum from I equals 1 to N.
Okay. So yeah, if you want to rewrite it as a sum using sigma notation, if that makes you feel better, then it is just kind of like I over n squared, right? And therefore, by the definition of integral, what is that?
There's a 1 over n.
So it's like 1 over N. It's like I.
Oh, yeah, this is harder. It's harder than initially appeared.
What's the question again?
What is this? What's the answer?
I like when you write it out like I times 1 over N.
Yeah, so some of you just get it, right? And the answer is, yeah, it's this. It's just the integral from 0 to 1 of x squared dx.
I didn't know that.
Oh, because it's like.
How do you know that? Because it just is, right? Because what is the integral from 0 to 1 of x squared? Well, you would be partitioning this from 0 to 1, and then you would be graphing x squared, which would be looking like this, and then this would be the area that you wanted, and then you would start at 0, and you would use n rectangles, let's say, and if you used n rectangles in the width of each one, delta x would be 1 over n, and then you just kind of like, first rectangle, that's 1 over n. Second rectangle, that's 2 over n. Third rectangle, the x value is 3 over n. And what would you do with all those numbers? You'd plug them into the f of x equals x squared graph. And so your last rectangle, your nth one, would be the last number you're adding, which is n over n, which is just 1. Now does this make sense?
Yes.
Okay, and what is this answer? Do you just know this one by heart by now? Or you just do it in your head? Answer?
It is 1/3.
It is 1/3. So thus, what I actually am asking you to do is to compute a limit. But each of these limits can be interpreted as the limit of a Riemann sum, which via the definition of integration is an actual integral. And now I'm asking you to go the further step of using the fundamental theorem of calculus to evaluate that integral and therefore answer the question about what the limit is. Does that make sense? Oh, I just like did it in my head. X cubed over 3 and then
Oh, yeah.
We already know that one. It's like
we
1
kind of
third.
already know that one, but yeah. And then all right. So should we do another one, or should I just let you like squirm? I think I'll just let you squirm. It's good homework. It's fun. It's fun. It's exciting.
It's homework?
Oh yeah, it's homework.
This whole packet?
Yeah, more also. Now we're gonna do the other 3 things I wanted to do today. Let's see, which are most essential.
I think I
Yeah.
forgot my agenda.
Yeah. Let's do this.
Oh my god, dude.
Edward, can you give everybody one of these? Alright, now that you guys are experts on the fundamental theorem of calculus, Sid, you okay? No? Forget something somewhere?
Yeah.
Yeah.
I lost my agenda book.
You lost your agenda book?
I just bought a new
Oh well, sorry. Sid. Looking things is terrible, but now I'm sorry. Okay, area and sector. Fundamental theorem of calculus, really important. That's why it has this kind of arrogant name, fundamental theorem of calculus. So, on the AP exam, which 5% of my job is preparing you for the AP exam, they are going to ask a lot of questions about the fundamental theorem of calculus because they want all students to deeply and fully understand it. Thus, on the AP exam, which consists of a multiple choice section and a free response section, and there are 6 free response questions that you will have about a year from now, one full question will essentially be, do you understand the fundamental theorem of calculus? And so I have compiled 4 problems, all of which address, in similar but slightly different ways, a deep understanding of reasoning regarding the fundamental theorem of calculus. So we're going to do one of these, possibly 2 of these, together right now. And then you're going to do the rest for homework. And then we're going to learn and understand, and there'll be a problem like this on our integration test, and there'll be a problem like this on the AP exam. It's going to be on HSA day. I'm going to talk about that later.
Is that next week?
Yeah, no.
Oh, wait, no.
Following week. Okay, so here we have a function. And it's important to read the direct, so this is not hard, but it is kind of abstract. It's not hard, but it is abstract. So here we go. I'm going to draw this. Begin reading the question as I catch up by drawing a picture. Yeah, let's do it. Okay, so here we have a function. Notice that this function that you are looking at is the function f. And then they define a new function g. G is the integral from 2 to x of f, so it's an accumulator function. And then they ask you a bunch of questions just to see if you even have any idea what the hell is going on. Like, what is g of 3? Well, by definition, what is g of 3 would be?
Integral from 2 to 3 of
f, which you can just glance at the boxes, count boxes. What's the answer?
3.
3. Am I going too fast? Good. What is g prime of 3?
Oh, it's just
F3.
G prime of 3 is, by the fundamental theorem of calculus, simply equal to f of 3.
that's 2.
And that is 2. Okay, good. What is g double prime of 3?
F prime.
That is, again, by the fundamental theorem of calculus, right? G double prime of 3 is simply f prime of 3. Yeah, are you cool?
It looks like negative 2.
And it looks like, in fact, it just is negative 2, yeah. Just by
Does it
looking
like
at
show
it.
work for that?
Not really, no. If it just is fine, you don't have to show any work. Just do it. Okay, good. Part B. Find the average rate of change of g on the interval from 0 to 3. Okay, now, Wilson, g is an accumulator function. But just because g is an accumulator function, don't freak out about that. Just do the problem the same way as you would normally have done any other problem. So if someone just walked up to you and said, hey, what's the average rate of change of g on the interval 0, 3? Wilson, what is that?
Just find
Do you want to answer? Yes.
It's like a kind of like an answer question thing. So like
Tried to call you, Wilson. Yeah?
so hold on a second. Average rate of change.
Wow.
But the rate of change of g is f, right?
Yeah, so that you're doing what I'm encouraging you not to do for the moment. Although it's possible to do so, it's probably simpler to Wilson. In general, if someone says, what's the average rate of change of g on an interval, what is that?
You just find the slope of
Oh, from point to point.
Yup, the average rate of change of g on the interval 0, 3 is the same thing we've been doing since basically the second day of calculus. What is it, Wilson, specifically?
The slope.
Can I get like numbers and letters and stuff?
Alright, G of 0,
What?
F.
G of 3
Yeah?
over.
Okay, you're trying to do too much, man. Someone else.
Oh,
Minus G of 0 over 3 minus 0. Agree or disagree? That's just how we define, that's just what the average rate of change of a functional interval means. I think it is much easier to just do it this way, because they're asking these very abstract questions and they're trying to like kind of test, do you really understand what you're doing, or are you just get confused easily? So I don't get confused easily because I know that the average rate of change of a function just means that. And now, simply just compute that, right? What is it? It's G of 3 is 3 as we just computed. What's G of 0?
0.
Well, that's actually a little bit complicated. No, it's not going to be 0. G of 0 is going to be the integral from 2 to 0 of f, which is
Just this like, it's like
not
negative,
0.
it's like upside
The
down.
integral from 2 to 0 of f is the opposite of the integral from 0 to 2 of f.
Backwards up. Upright.
And the integral from 0 to 2 is 4, because it's like 1/2, 2, 4. So this is negative 4. Are you guys with me?
Yeah.
Okay, so this is 3 minus negative 4 over 3. And in fact, therefore, the average rate of change of this function is just 7/3 on this interval. Yes?
If you like mess up in part A what G of 3 is and then you use that in part B,
Yeah,
that takes
then
more
you're
time.
screwed.
Yeah.
Yep, so don't mess up. Alright, Ethan, did you, now it is also possible, but not recommended,
Why isn't it?
it's possible, but not recommended, to think about it a lot more, and you can say, okay, well, if you want to know the average rate of change of G, I think this is what you were saying, right? The rate of change of G is actually just f. And so by asking what the average rate of change of G is on this interval, it's sort of like asking what the average value of f is on this interval. And that is an alternative way to do this. To answer the question, what is the average value of f on the interval 0, 3? And if you did that, that would be 1 over 3 minus 0 times the integral from 0 to 3 of f. And what is the integral from 0 to 3 of f?
1, 2, 3.
You count boxes, it's just like 7. So this is 7/3. So you would also get the answer that way. So that is an alternative way to do it. You can just know how to compute the average rate of change of a function and then just do it. Or you can think that the rate of change of G is f, and so the average rate of change of G is just the average value of f. Do you guys see the two? I guess both ways are good. Okay, more. Part C. Now comes another kind of abstract sort of question. For how many values of C on the interval 0, 3 is G prime equal to the average rate found in part B?
Can we just do this?
Can someone translate this strange language for me? Yes, how often is G, basically they're saying when, for what x, so how often, they're basically saying how often is G prime of x equal to 7/3?
And G prime of x is f.
And G prime of x is simply f. So really they're asking how often is f 7/3? How often is f 7/3 on the interval 0, 3?
Once. Twice.
Twice, right? Because 7/3 is like 3 something.
This show always explain.
Yeah, some explanation is needed because they say explain your reasoning. So you just have to say something like, you have to say something like G prime of x just is f of x. Okay, that demonstrates that you understand the fundamental theorem of calculus. There exists, and then first you should probably answer the question. So twice on the interval 0, 3, G prime of C equals 7/3. You know, because G prime of C is just F of C. And I don't even think they want numbers. You can just say, and by looking at the graph or something, or by inspection, they like that phrase. By inspection is kind of like a way of saying, I just looked at the graph and I can see F of C equals 7/3, you know, twice on the interval 0, 3. Something like that. That's probably even more than sufficient. Are you guys with me? Okay, can we do part D? All right. Part D. Find the x-coordinate of each point of inflection of the graph of G. Everyone think about this for a minute. Let's be a little bit careful about that.
No, this is actually signed. Yes. By inspection.
All right, so what is a point of inflection of G? When will G have a point of inflection? By the definition of point of inflection, although different textbooks differ on this. When the second derivative changes sign. Yeah, you essentially have three alternative definitions of point of inflection. It's either when the concavity changes, or you can, I guess you could just define it as when the second derivative changes sign, or I don't know, whatever. But basically, the way we did in this class is, point of inflection is when the concavity changes, and you find one by saying that G double prime changes sign. But of course, what is G double prime? F prime. So we're looking for where F prime changes sign. Where does F prime change sign? At 2 and 5, exactly. F prime is just the slope of F. F prime is positive, then F prime is negative, then F prime is still negative at 4, and then F prime becomes positive again. So if you write 4, you know, minus all the points. Because it's not just when F prime is 0. In fact, it's not even 0 here, right? It's like undefined or something. But anyway, it's where F prime changes sign. So the answer is, you could say something like, I don't know, there's many different ways to write this, but you should probably first answer the question. At x equals 2 and x equals 5, because that's where G double prime, you know, which is F prime, something like that, changes sign. And then, yeah, good. That's pretty much good enough. All right, so you have to look carefully, and you have to see where sometimes they say explain your reasoning, in which case a sentence is needed, or a sentence fragment at least. And sometimes they don't say explain, and then don't waste your time explaining. All right, I think these get kind of progressively harder. Maybe I'll have you do like 2 of them, and then we'll go